Restart for this afternoon's sessions. Thank you very much. Hopefully everybody had a full and satisfying lunch period. And now that we're back in it, I would like to give you a couple of more administrative comments. We are going to have the pleasure of having the administrator of NASA, Charlie Bolden. He's going to join us at 4 p.m. today. So we've just gotten confirmation of that. So it's extra important that we stay on task, on time, and everyone has done an excellent job this morning, and we're going to continue that through the afternoon. We have two panels for you this afternoon. I'll come up in between each one, but I'd like to, I have the honor of introducing Paul Abell from Johnson Space Center. He's a space scientist down there. He's going to be the panel leader and moderator for our next panel, which is Lessons Learned from NEO Missions, and he'll be the prime facilitator, and we'll introduce each of the panelists.
Okay, good afternoon. We have four presentations basically dealing with previous missions to near-Earth objects. The first is on the NEAR mission by Andy Cheng. He's the chief scientist of the Space Department at Applied Physics Laboratory. Then we have Lindley Johnson, who's going to be speaking to us about the Deep Impact mission, and he's the was the program executive officer for the Deep Impact mission. And then to talk about the lessons learned from the Hayabusa mission, we have Professor Kuninaka from the Japanese Aerospace Exploration Agency. And finally, to follow up, we have Marcello Coradini from ESA, and he is the head of the Robotic Exploration Office. So the first talk could be with Andy Cheng.
Okay, thank you. It's great to be here, and I'm going to be talking about the Near-Earth Asteroid Rendezvous, or the NEAR mission, which was, as you show here, the first launch and discovery program, and also the first mission to an asteroid, first mission to orbit one and to land on one. But I wanted to mention that one of the great benefits of the NEAR mission is, in fact, represented by the people here, because there's a lot of alumni from that mission in this room, starting with Paul Abell himself. And I'm just looking in the room, I see Clark Chapman, I see Jim Garvin, Rob Gold, Don Yeomans, Jay Jenkins, who mentioned earlier. They're all people who worked on the NEAR mission. So anyway, and myself, of course. I was a project scientist. Okay, next. Oh, I'm supposed to hit the button. This one? Yeah. Aha, okay. Well, a quick summary of the NEAR mission. Launch was in February 1996. I can't believe it was that long ago. But immediately out to the Matilda flyby, which was the first spacecraft encounter with a C-type main belt asteroid. Then Earth swingby, and a bad day when we were in December 1998. Our first attempt to enter orbit around Eros was not successful. I'll come back to it. So we had to go one more time around the sun, and then encountered Eros again in February 2000. The picture there is how Eros looked on approach, and that's a little rotation movie on approach. Then rendezvous, and at the end of the mission, asteroid landing and continued science operations. Okay, so I've already mentioned all of this. Many other, first, it was the first planetary mission at APL. Also, it was the first planetary mission outside of a NASA center for, forever and ever, practically. Some other cute things, again, NEAR was started right around the time that the internet came into wide use. And so one of the things that we did, it was one of the first blogs, one of the first AOs for the NEAR Participating Scientist Program that was issued by internet, and use of internet email instead of letters to announce science team meetings and to send minutes out and things like that. So all these. Also, we were one of the first missions that had an open data policy requirement along with the Mars Pathfinder. That was new. That was difficult, in fact, for some of our science team members to accept, but okay. All right, some more about NEAR. NEAR was one of the faster, better, cheaper missions. It worked. It's not as if everything went well on NEAR, as I will get through, but we overcame the difficulties that we ran into. But NEAR was a 27-month development from start to launch, so some authorization to proceed to launch, less than 27 months. And in $92, that cost was actually under $110 million. This is exclusive of launch vehicle, and it's up to launch plus 30 days, included the payload, and whatever. And I'll talk more about the spacecraft and the payload. Launch vehicle was the Delta II 7925. Okay, so I'll say a little bit about what we did there. It was a basic characterization: shape, mass, density, gravity field, spin state, magnetic field. Did not find a magnetic field, which was interesting. We did not know why. We still don't know why, really. There isn't a measurable field there. And also the important properties of the surface, what it's made out of, and the surface geology. Didn't really know what to expect at an asteroid, and indeed what we found was surprising. Okay, I think I've already mentioned some of the management processes that enabled it all to come together. Short schedule helps, of course. I mean, as a low-cost mission, short schedule helps. Small team with authority, and you delegate your authority down as far as you can, so that that people are empowered to make decisions when they know that because they have the knowledge down there, and as long as they can accomplish what they need to do within the resources that have been allocated to them, let them go, let them do what they need to do. And the mission, the spacecraft is not fully redundant, but pretty close. And so a reliable, redundant, spacecraft, lots of backup systems, you can do that within a small, low-cost mission. And another very important thing, which I need to mention, the single agency manager interfacing with the contractor. Very key, very key. And so that's what we had also at NASA. That was very helpful, that there was a program executive, actually a few program executives we had, that was our interface to NASA, and not a huge team monitoring and managing us. Okay. The payload. The payload actually, I won't dwell on the details. Anyway, visible imager, X-ray, gamma ray spectrometer, near IR infrared spectrograph, magnetometer, laser altimeter, and a radio science experiment to do the basic measurements that we needed of shape, rotation, surface morphology, that's imager, geology. The next two instruments, X-ray, gamma ray spectrometer, and infrared spectrograph. Composition instruments tell us what kind of materials you find on the asteroid, and are they primitive or evolved? That was the big question for NEAR. Magnetometer to look for a magnetic field, laser altimeter, topography, and also navigation. This payload was, in fact, the payload that was defined by a 1985 NASA science definition team. It was that payload. They recommended an additional instrument as a nice-to-have, which we did not accommodate. Only one. That was a thermal mapper. But all the other instruments that were recommended, including one extra, which was a laser altimeter, that was also a nice-to-have instrument. But the rest of the payload was accommodated. And the other interesting thing you see in the corner here is that this presentation actually predates PowerPoint. So we don't have this as a PowerPoint slide. It's actually a view graph, a plastic view graph that we had to scan, because there's no electronic version of this otherwise. So that's 1992. Okay, it was an APL spacecraft. It was facility instruments. NASA did select a facility instrument science team. The reason, and also subsequently, NASA selected a participating science team. So we ended up with a fairly large science team, which was good. I mean, that really enhanced the science output. And this procurement strategy was done this way because of the need for speed. This was as one of the first two missions in the Discovery program. NASA felt the need to get it going, get data back fast, and make sure that we were successful. So The judgment was there just wasn't time to fully complete the science payload. They felt that would put too much program risk and would take too long. Okay, so APL mission operations and also JPL navigation, DSN support. Okay. Picture of the spacecraft, the same. It's, I don't know how much I probably don't need to go into too much detail, but it's a simple spacecraft, solar powered, 3-axis stabilized, dual mode propulsion with a moderate delta V, 1450 meter per second, and capable of going out to a couple of, 2.5 or I think 2.6 AU from the sun. So that's our maximum distance from the sun. It's interesting here, the schedule. This schedule was set by the program manager, Tom Coughlin, in 1992, and it was, we followed it through launch. This is correct. And it was, very important to that, not only the management practices at APL, but I think also that the environment, there were no hitches, big hitches in the funding from NASA, no problems, program delays. So the stars aligned in some sense to allow this to happen. But it actually, once in a while, you can set a schedule at the beginning of a program and actually follow it. Isn't that amazing? So, okay. I think I've said most of what we have talked about already. Yes, this is a discovery mission that worked. It was a design to schedule. So, yeah, be careful in large use of COTS components and all that. All right. What is this? Okay, so I think I've said all of these things. We're now getting into some of the results. Yes, into orbit and landing and landed science operations. Okay, the bad day we had. We did have a very bad day. It's not as if everything went well on this mission. But December 20, 1998, there was a few seconds after the first of the big rendezvous burns. Spacecraft went into a safe hold. We lost contact with the spacecraft. We went through one very terrible day not knowing what was going on. But the spacecraft autonomously recovered in a way that we still don't fully understand because no, it was because the solid-state memory was erased so that the housekeeping data, Jay can probably tell you about this. But anyway, so we have visibility only into the very beginning of the process because some of that data was downlinked. And after that, we don't really know what happened. So despite lots of investigations and simulations, not really sure why the spacecraft recovered, but it did. And it expended 28 kilograms of fuel, and despite that, there was still enough fuel in the spacecraft to do the mission. So we could credit Bob Farquhar for that. Bob, by the way, was the person who first came up with the near mission to Eros. He was one who identified the Eros opportunity. Okay, other lessons learned. We had to learn how to do the mission in flight because there was no other mission to orbit a small body previously. When we went there, on the way there, we did not even know the mass of the body very accurately, so there was no way to predict the orbits. So you could not do the kind of detailed orbital planning that you do on a Cassini or a Galileo for years in advance. You decide every single operation you're going to do. That's just not possible. So, and again, that's something we'll have to do again. The next time you go to a small body, you're still going to be in the same situation, that your detailed orbital plan you have to do almost in real time. When you get there, you can have an idea of what you're going to do, you can have things in place, and you can be ready, but you have to make measurements, basic measurements of the body, its rotation, its size, its mass, and so on. You've got to turn around the data analysis very quickly, and then make your actual plan. Okay. Science team expected that our data return would be limited by safe holds. I mean, surely something bad would happen. I mean, after all, they'd already experienced one very bad safe hold when we just tried to get into orbit. Surely it would happen again at the asteroid, but it did not. Everything went very smoothly. So, anyway. So yes, the Eros flyby was a blessing. It gave us an extra year to think things over, to get our operations, to get ready for operations around the asteroid. Also, the flyby gave a rough, very rough idea of the mass. So we had an idea. Instead of being a factor of 2 or 3 uncertainty of what the mass was, it was down to around 20%, which helped a lot. Okay. And in the end, I only have a little bit of time left. Mission success. Final cost was very close to what was originally predicted, and the data return was actually far greater because of the lack of safe holds and so on. The total data return was much greater than originally expected. Landed, even though the spacecraft was not designed for that, but of course the orbital velocities of these tiny objects are very low, so even if you land at close to orbital velocity, it's not that fast. And then the spacecraft continued to acquire very critical scientific data. The gamma ray spectrometer data, the best data, were obtained on the surface. It showed that Eros material is primitive. It's not differentiated. It's not a body that has ever been melted and separated into different components by depth. It's primitive. It's like the kind of meteorite that we call the ordinary chondrites, which are some of the most ancient materials in the solar system, preserve things from the beginning of the solar system and even little bits from before the solar system. Anyway, on the surface of Eros, okay, I'll skip that. Geology that people never expected. It's an active surface. These are not just dead rocks, but things are going on now. We have, here's another example of a really striking scene. We have a pond at the bottom, and above that, a debris flow. And just a final lesson that we have learned since then, this is not near, but this is the only other asteroid that we've been to up close and personal, which is Hayabusa, and we'll hear more about that later. But the asteroid is Itakawa. This is Itakawa, and obviously, just from looking at those pictures, totally different kind of beast. Okay. Thank you.
Hold questions. We're going to have a discussion period at the end of this session, so you'll have time to go to the microphone and ask questions. So next is Lindley.
Sorry you got to listen to me twice in one day, but you're on my playground now, so you're going to see me occasionally. Wasn't able to get most of the team for Deep Impact to come talk to you today. They're either on vacation, or a lot of them are actually in planning sessions for the next encounter that the Deep Impact spacecraft has, which is coming up in less than 90 days with Hartley 2. So they've got a science team meeting this week on that. So I'll be able to spare you all the litany of science and discoveries of what we learned about comets, and maybe more importantly, what we found out we didn't know about comets with this mission. So let's see, get my clicker up here. So our lessons learned. Well, first thing about this mission is Temple 1, which is our target comet, is not a near-Earth object. It only comes a little bit inside Mars orbit, and that was where the encounter took place. Mission launched in late December of 2004 and had the encounter with the comet on July 4th, 2005, just for a good celebration of the American independence. It was a short mission, six month mission, but we've got a very good spacecraft, a very sturdy spacecraft, and that's why we're still flying it today in 2010 for a rendezvous with another comet. Here is the spacecraft, actually the spacecraft plural, because one of the things we found out, even though this impactor was meant to be pretty simple, just a 400 kilogram mass to impact the comet and dig out a lot of the material, we've found that it actually had to be a pretty sophisticated, smart projectile. So we really found out that we were flying two spacecraft. The mothership or main spacecraft had a fairly simple instrument suite, although there are complex instruments, but basically 2 telescopes, a high-resolution telescope with a IR spectrograph on it, and a medium-resolution telescope. The Impactor also had an imaging system for doing its terminal correction and impacting the comet. This was during testing at Ball Aerospace, and then this was the image taken as the 2 spacecraft were integrated right prior to shipment to Kennedy. The mission scenario here was really pretty simple. It really was it was the old schoolboy trick of tossing a penny in front of the semi and seeing what happens. Because in truth, we did not impact the comet. The comet ran over us, and we're waiting for the solar system court to open so we can file charges. But our spacecraft came along, tossed off the impactor. It did its vectoring in and changed its course had 3 different course corrections to bring it in so that it was in the right place for the comet to run over it. And then our main spacecraft did a divert maneuver so it could get out of the way and then observe the impact on the comet from several different angles here. We had to go into a shield mode at this point with our solar panel in front of us so that we would minimize any possible impacts to our spacecraft so that we would survive the encounter and be able to downlink our science data after the encounter. So here was the target, a comet, but boy, we sort of amazed to see this thing. Our initial thought was we've gone to the wrong target because this doesn't look like what we thought a comet would look like because you got craters down here. What comet has a surface that lasts long enough to have craters? So this is evidently some older surface down here. We've got some layering here on the comet. Maybe this is a slump region up here. This region up here happened to have a lot of water on it. We've got some kind of a flow here, but we don't know whether it's proceeding or receding. So there's a lot of interesting things to look at. Also, there was a lot of more predominantly CO2 ice in the southern hemisphere versus the northern hemisphere. So there's definitely some differences across the surface of the comet. So that was all very interesting. The discoveries that the scientists will be spending years studying and learning more about. So were you able to load up my movies there? Let's show the first movie from the Impactor approach. This is kind of a la Lunar Ranger. I know key principle of education is if you can't teach them anything, at least entertain them. So this is the approach. These are imaging from the impacting spacecraft as it came in to the comet. Why don't you play it one more time here? This is from about 5 hours before to actually impact. You can see it kind of changed position on kind of a jerky pattern. So that was the impactor's demise. Why don't you go to the second one now? This is the imagery from the high-resolution imager. Run it one more time for us. You can see that plume as the impactor hits, and then all this stuff that came out of the comet. And once you go to the medium-resolution image of the last one now, gives it a little slower, and you can see perhaps a little more detail of that plume, and then the explosion of all that ejectile. This material, from what we've been able to learn about it, was a lot finer than we were expecting. This is talcum powder, fineness, and it remained, continued to expand and remained around the comet for hours and actually days. So those are all some things to consider before you go messing around with a comet. Next slide, which I can get to. This was talking about the terminal guidance on the impactor. It was all autonomous. We just did not have the time for the real-time loop for guidance from the ground. This was at 83 million miles. Case. But anyway, when it was released, it was kind of aimed at this point, and the impactor was designed to go for the bright spot in simple terms. So we don't know what happened on the first one because it aimed down here. Evidently saw something bright and dangly down there that it wanted to go after. But then with the subsequent 2 corrections, we got back on the comet and then into the spot where you saw it eventually impacted. We're anxious for our Stardust Next mission, which again is a repurposed spacecraft going to another target after its prime mission was over. Stardust Next is returning to Temple 1. The encounter will be February 14th, thanks to Bob Farquhar. And we are really looking forward to seeing more of this comet, first of all, and how it has evolved since we visited it in 2005. And hopefully, if everything works out right, we'll be able to image the crater that we made. That'll be exciting. Okay, I think I missed it. No, guess not. Oh, so we are to the lessons learned now. A lot of lessons learned, of course, but I just want to hit a couple of major points. And the first one is plan to be surprised. Temple 1 didn't look like what we thought it was going to look like. It didn't react to the stimulus quite the way most thought it would, although some on the team had this peg, or at least they say they did anyway. Now, and the material, as I said, was much finer than we were predicting from this body. Now, I should have said Temple 1 is about a 3-kilometer body, so it's a little larger, has a little bit more of a gravity field than maybe some of the small stuff that we'd be looking at initially. But this all probably means that precursor mission, hit the right button here, precursor mission to the specific target body you're looking at is probably a must unless we've been able to get good remote observations by some other means to have confidence in mission success and safety of the crew and operations around that target. At least some kind of a reconnaissance mission, and it might be, of a scout class. It doesn't necessarily have to be a fully instrumented, scientifically robust spacecraft to do that recce. Now, I'm not saying that you don't need to do extensive pre-planning activities and exercise events to an nth degree. Because all of that will help you establish your baselines and know what your capabilities are and what you can do, and then you're able to plan from that as things come up. So it helps, you've got to do all this work to establish what your baselines and capability and timelines and sets are. But it does mean you have to have a well-established and exercised process to be able to handle that unexpected, because it's going to happen, and you've got to be able to replan dynamically during the mission. Thankfully, that's one of the things that humans are good at. So we look forward to working with you all more on this. Thank you.
Okay, next, Professor Kuninaka.
So I have already presented the status of Hayabusa, so that this presentation focus on the lessons learned of Hayabusa mission. And then so Hayabusa uses the low and continuous thrust for the orbit trajectory. So in comparison to the impulse maneuver, so that is one of the difference for the that is a very special feature of the Hayabusa space missions. And then so I want to focus on the lessons learned for the trajectory maneuvers. And then so I want to summarize the, I want to show you the three items. One is the attitude control, and the second one is the a trajectory maneuver, and the third one is the TCM. TCM means the trajectory correction maneuvers. And then so as for the attitude control, we have some problems in space operation. You can see this table show you the time-dependent malfunction. First one is before the rendezvous, we lost one of the reaction wheels. And so originally Hayabusa installed the 3 reaction wheels. And so at that first malfunction, we executed the countermeasure to change to the 2-wheel mode after the first loss of the reaction wheels. And then so in the September 2005, we caused the second reaction wheel loss of the second reaction wheel. At that moment, we changed the short pulse operation of bipropellant thruster, so-called the zero momentum method. And then so after the touchdown operation, we lost the function of the bipropellant thruster. At this moment, we executed the establishment of 3-axis attitude control by a single reaction wheel and ion engine thrust vector control. In that sense, the Hayabusa has enough redundancy, but some of the redundancy was developed after the malfunction, including the improvement of the onboard software and ground support system. And then so this chart shows you the method for the xenon cold gas jet attitude control method. So I have already explained you, but so you can see we have 4 ion engine, and so and 4 neutralizer. So as for the neutralizer, they are set in canted direction, and so that the exhaust gas from the neutralizer is a very, very tiny one, and so our single neutralizer ejection of the gas from the neutralizer generates the order of 10 micronewton, very tiny thrust force. But you can see a relatively long torque arms, so that the control torque is enough for the attitude change of the spacecraft using even in this technique. And then so we have a 4 neutralizer, and so that the combination of the neutralizer, we can generate the a lot of in the 3 rotational torques, depending on the any combination of the 4 neutralizers. This is one of the techniques for the re-establishment of the attitude of spacecraft. Now, another one is I have already used this chart. So in the maneuver of the ion engine, so we re-establish the 3-axis control using the single reaction wheel and ion engine thrust vector control and xenon cold gas jet and solar pressure torque. So that using this technique, we establish the 3-axis control of the spacecraft. And third one is a delta V maneuver. This function is the depend on the function of the ion engines. Basically design 3 thrusters are dedicated to the round-trip space mission. And then fourth one is a redundant ion engine. And so that we installed 4 ion engine. But just after the launch, thruster A has something trouble. So that's we decided to not to use thruster A. And then final phase of the return mission of the Hayabusa, end of 2009, all of thruster has something trouble. In that sense, we executed the combined operation, ion source B and neutralizer A. We kept the delta V maneuver at the all of the round-trip space mission using the ion engine. This figure I have already explained you the cross-connected operation of ion engine. Neutralizer A and ion source B are combined to the synthesized ion engine. And then a third one is a TCM, trajectory correction maneuver. That is a very nervous operation to targeting to Earth, especially point-wise landing. We need very precise maneuver in space. And then original plan, we plan to use bipropellant thruster for TCM, but you may know we lost function of that bipropellant thruster at the proximity operation of the asteroid Itakawa, and then we swapped to use ion engine for TCM. And then first, I have already said to you, Hayabusa uses the low and continuous thrusting for the orbit transfer. And then in that sense, we have a relatively long time to change the orbit. And then we have a lot of way a lot of scheme for the orbit maneuvering. And then once we have troubles in the space mission, we can establish, plan, orbit maneuver plan using the ion engine. That is the completely difference to the impulse transfer scheme. And based on that scheme, we reconstruct the orbit plan using the ion engine, and finally we succeeded to the round-trip space mission of the Hayabusa. Okay, that is the final page. For the lessons learned of the Hayabusa, Hayabusa has enough redundant method for the orbit trajectory, including the ion engine and the reaction wheel and the bipropellant thruster, and so on. That's all. Thank you.
Okay, next we have Marcello Cardini.
How does it work? Oh, okay. Thank you. So, good afternoon, everybody. As you see, I'm presently and for another couple of weeks head of the robotic exploration of ESA. I am moving now as an ESA representative at JPL. ESA has a huge amount of business with JPL, so we thought that it was absolutely necessary having someone coordinating all the large number of missions across the board that we have with NASA and JPL. So this was just a small personal announcement. But anyhow, let's come to the ESA activities about asteroid. Let me start that despite the fact that we have quite a number of data and, let's say, images and activities in asteroidal fields at ESA, we never had until now a specific asteroidal mission. So everything came from as a byproduct of missions devoted to other goals. Why that? Well, in every organization like NASA as well in ESA, we have a science directorate, exploration directorate. So when it comes to a competitive system to select a science mission, An asteroidal mission is a kind of a monochromatic mission that serves a community which is smaller, for instance, than a community, the large number of communities that can be involved in the exploration of Jupiter, the exploration of Mars. You go from atmospheric physics to geophysics to plasma physics. When you study asteroid, you study one single body in a one single way, spectroscopic assessment from orbit, mineralogy, and that's it, basically. So the legacy in support of an asteroidal mission, at least in Europe, has always been smaller. In a competitive system, within the science program, they always lost. When you go out of the science program, people start saying, why should we pay for this mission? This is an applicative mission that covers aspects, societal aspects, which go well beyond the competence of a space agency. And until now, unfortunately, organizations such as civil protections, defense, Ministry of Defense, and so on, haven't developed a sensitivity for developing techniques and supporting missions for planetary defense. So in Europe, at least, I don't want to generalize, these missions have always been falling between the cracks. So at a certain moment, sometimes in year 2000, towards 2003, 2004, we decided to organize a number of meetings in order to raise the level of attention on asteroidal mission and potential threat, and also with a goal to possibly raising the level of attention and the level of funding from different organizations than a single space agency. And in doing that, we eventually, the outcome of all this activity that we carried out in Europe was the definition of a strategy, of a stepped approach to the exploration of asteroids and to the, let's say, management of the potential threat that comes from the asteroid. So we have identified 4 steps. The first 2 steps are for the assessment of the bodies, understanding the bodies, compiling catalogs of the bodies. And the other steps are the real implementation of a defense system. But between step 1 and step 4, probably there are something like between 10 and 20 years of activities. And as I said, the contribution that ESA is given to this kind of activities comes as a byproduct of other missions. Very soon we are going to launch, and this is an example, we are going to launch an astrometry mission which is called Gaia. A byproduct, which is extremely important, is the capability of this mission to basically complete the assessment of let's say, asteroidal discovery well below 1 kilometer. So without having a dedicated observatory, still with another kind of a telescope, we'll be able to go down and to complete the assessment of the populations. And this is a major contribution, even if we cannot call Gaia an asteroidal mission. When we go to further steps, we have other missions which have provided a strong contribution, and specifically, going quickly, one of the first contributions is the joint ESA-NASA Cassini mission, the World Asteroidal Flyby. But most, and in particular, is the Rosetta mission for us. Rosetta is a mission dedicated to the exploration, eventually to the exploration, in situ exploration of a comet. But going to the comet, we have already flown by 2 asteroids. So we had the flyby a couple of years ago of an E-type asteroid, Steins. These are the images, and part of some of what you see here is the spectra taken with different filters from the high-resolution imaging system on board of the Rosetta mission, the camera developed by Uwe Keller. And very, very recently, we had the flyby of Lutetia, which has already been mentioned in other presentations. What I want to underline about Lutetia is that, again, if we base our understanding of asteroids simply on remote sensing, the information can be misleading. Even when you go to homogeneous families, families based on mineralogical common denominators or dynamical grouping of asteroids, you can come to wrong conclusions. And we have also seen that all the asteroids which have been flown by until now, even if they are similar in composition, they have a morphology and a geological structure which is incredibly differentiated. And Lutetia was a classical example. Lutetia was considered a transient body between a carbonate chondritic and a metallic asteroid? Well, once we fly by and we look at the spectra, we actually realize these are very new data that I received this morning from DPI of the instrument of the infrared spectrometer, who happened to be my sister, so I have an easy access to the data. And what you can see is that you have three different parts of the spectra, and particularly on the right-hand side, you have the possibility, and they are working on that, of compiling the thermal behavior, calculating the thermal behavior of the body on the visible part, and in the central part, there is no evidence of metal. And this was considered a metallic asteroid. So we gotta be extremely careful when we base, for instance, missions on knowledge which is exclusively based on remote sensing. So this is a lesson that we have to learn. But obviously, just flying by asteroids is not enough. I think that we need to develop two missions, and we have studied this type of missions at ESA very recently. One is how to, let's say, manage the possible threat of an asteroid that may collide with the Earth, and this is the Donkeyshot mission, which consists basically of two different spacecraft, we'll see it later in the presentation, trying to deflect well in advance the asteroid with non-destructive technique. And the other one, and I think it's fundamental, is a sample return mission from an asteroid. In all the exploration programs, we have sample return missions, basically from Mars. Mars is a very difficult planet. It has a large gravity, it has a moody atmosphere, and returning sample, every year we postpone the Mars sample return mission of 2 years of a launch window. So maybe the question is, can't we test before going to Mars a major asteroidal sample return from one of the asteroids? We tried to do that. Unfortunately, the collaboration in the framework of the competitive selection of the new mission of the Cosmic Vision long-term program, the collaboration with JAXA was not too successful for a number of reasons, and nobody's responsible for that. So unfortunately, when we presented the Marco Polo mission, an asteroidal sample return, as a standing alone mission, could not be selected because it was too expensive. And this is another message that I want to give. When we talk about asteroidal missions, they are not cheap. If you want to do something meaningful, these missions are not cheap. Just to give you an example, the data that you have seen from the spectrometers flying on Rosetta, that spectrometer cost in present money something like 45 million. So when I saw that you present a budget of 200 million to go to an asteroid, I can tell you 100 millions are for the payload. And then you have to do, if you want to have a meaningful payload from a scientific point of view, then you are left with 100 million. So either you ask international collaborations to invest the other 400 million to do the mission, or you don't do the mission. Rosetta lands on a comet, okay, and has flown by 2 asteroids. Rosetta is a 1 billion mission, and the payload is in the 150 million ballpark. The lander, we didn't pay for the lander, it's a contribution from the member states. The lander is another little investment of about 100 million. So these are big numbers when it comes to missions to such small bodies. However, the importance of Rosetta, for instance, also for asteroidal mission, is that we will learn how to operate a spacecraft on the surface of a body which is basically zero friction and zero gravity. So we have to enter in a completely different mental framework. I heard in one of the presenters saying, we want a rover on an asteroid. On an asteroid, you have basically no gravity and no friction, so you don't drive a car. It's like asking an astronaut to walk on the solar arrays of the space station. You cannot do it. And if you put an astronaut on the surface of an asteroid, particularly if the asteroid is small, you have to tether the astronaut because it's exactly an extravehicular activity. It's not walking on a surface. So imagine the complication of having an astronaut that has to have a tether which is attached to a lander which is in communication with a mother spacecraft. So it's not a simple business. Technology is huge to develop, even to go to an asteroid. Coming back to this view graph, I always prepare view graphs and I never follow them. The Donkeyshot mission. The Donkeyshot mission is another study that we made. This is in terms of planetary protection. So it's very similar in a way to what has already been done with the deep impact. And the lesson is, if you cannot increase indefinitely the mass, because we have clear limitations in the launching capabilities, you have to increase dramatically the impact velocity. And you have to decrease as much as possible the size of the body. The problem is that Mother Nature not necessarily decides that the body is small, and not necessarily we can find the body so early that we can take 10 years to develop a mission. So there are societal problems, even if we know that we can deflect a mission, impacting it at 10, 12 kilometers per second with a decent amount of mass. Most likely, if the body is small, with the present technique, if we don't develop more monitoring techniques of asteroids, we'll find out about this body 5 or 6 years before it becomes dangerous, maybe 10 years. But if you look at the time needed to develop a simple mission nowadays by any agency, is between 5 and 7 years. And imagine working under a panic situation, knowing that this body is falling on our head, and having to develop a mission which is not small. It's an important mission. So we have this type of societal approach that is missing today. And this leads me to step 3 and 4, which is once we have a complete catalog of all the bodies, not only up down to 1 kilometer, but down to 100 meters. We need to monitor continuously the orbit of this body. Discovering the asteroids is simple. Monitoring the asteroids require a network, a worldwide network. Why? Unfortunately, the Earth is round and spins around, and the body is not always visible, and we have clouds, we have meteorology issues. So we have to have lots of observatories all around the globe in order to track all these bodies. Many of them, they are discovered and then they disappeared. Why? Because we don't have enough data to go and look for them again after 1 or 2 years. So the lesson is, step number 3, having a monitoring system, ground-based but also space-borne, that allows continuous monitoring of the bodies, a continuous compilation of their orbits, a variation of their orbits. And then it comes the other potential players. As I said at the beginning of my speech, if we only have a space agency, when it comes to a societal process or problem, we don't have enough funds, we don't have the culture. We cannot deal with the risk, with the information of the risk and the management of the risk. We have to appeal to civil protection. We have to appeal to the Ministry of Defense, but not only for managing the risk and the communication, also for funding the missions and funding the technologies in preparation of this. How the human enterprise may enter into game here? Well, let me improvise a little bit. Very recently, the advanced study team at ESA has done a little assessment of what would be required for a human missions to an asteroid. So they took the large number of asteroids, they decreased it with this type of parameters. The flight time has to be short for obvious reasons. The body cannot be too small but not even too big, because otherwise we have too much gravity and becomes just like a planetary mission, and so on and so on. So when you apply all the limitative parameters to this, the number of asteroids which can be possibly visited by human beings becomes very small. And however, I think that in terms of planetary protection, considering that not necessarily if the body is larger than 500 meters, we will not probably be able to deviate the body. But, well, maybe in this case, the added value of a manned mission is that the astronauts can deploy maybe motors that push the asteroid continuously for 5-10 years in such a way that over a long time, a tiny deviation allows even a big body to avoid the impact with the Earth. I think that this is one of the major added value of a manned mission. Probably with robotic missions we could do it, but it's extremely difficult to do it because you need lots of missions. 3 men can do the work of 10 or 15 robots or 10 or 15 missions. So there is a chance. But with all the caveats that I said before, you are going to a gravity, to a body without gravity, and so the mission is extravehicular mission. So I'm finished, and all what I said can be found on this book that I can give to everybody for free. If first come, first served, I still have about 100 books in my office. If you are interested, send me an email and I will send you the book. Thank you.
Okay, we have some time for discussion. If you have a question, please come to the microphone. And we have 4 distinguished panelists here who will be ready to answer your questions. Anyone? Okay, let's do something a little different then. I'd like each of the panelists to highlight one of the major lessons learned of their particular program, or things that we would need to know for future robotic missions. And we'll start with Andy. Just take a minute. Use the mic. You can use the mic.
Right there. Okay. I just want to remind people something we have said, which is that so far only 2 spacecraft have contacted an asteroid. And as we just heard, one of them was seriously damaged in the process, so that when it came back, the biprop system did not work anymore. It was a propellant leak. We don't really know what caused it. The other spacecraft that landed on an asteroid was able to operate for 2 weeks, but we never tried to lift off again. So we operated an instrument, we communicated with Earth, and then we turned it off. So I'm not sure what the lesson is to learn, but again, echoing the comment that Marcello just made, it's maybe not so simple to be on an asteroid and operate safely.
Thanks. Lindley?
Well, I think in all of this, there is still a lot of spade work to be done to understand, first of all, what our target set is and what the best destinations in that target set are for a manned mission, a human mission. So I think there's we need to sit down together and put together a logical roadmap to accomplish those things. And I think we're off to a good start here, starting off with a workshop like this and working through those steps over the next few months to a year here or so. First, before we launch off in some direction, not knowing what it is we're really looking at is very important.
Thank you. Professor Kuninaka.
Yep. For my presentation, I focused on the trajectory operation, but in the proximity operation around the asteroid, so in case of the robotics operation, we need the autonomous operation, so that the maybe spacecraft will arrive at the will rendezvous around the asteroid extremely far away Earth, so that the spacecraft should possess the autonomous operation. And then so in the another aspect is the if we execute the sample return, in that case the sampling mechanisms or sampling method is we need some invention for that items, I think.
And Marcello.
Just a consideration about energy requirements for these missions. Nobody mentioned until now the fact that we have incredible limitations with solar arrays. They're big, they vibrate, they make the spacecraft unstable, and if you are on the surface and you want to stay on the surface for a long time, an asteroid spins very quickly, and so you have a very low, let's say, production time for energy. So I think that the way ahead is, again, making major investment in methods for production of energies alternative to solar arrays, which means basically nuclear production, and not RTGs, but real production of power with miniaturized nuclear power systems because otherwise we are limited in time, we are limited in space, we are limited in lifetime of the mission.
Okay, thank you. Okay, we have a couple of questions. I think that's a little bit out of the purview for this particular topic, so maybe we can table that for a later discussion. So, do we have time for other questions, or how are we on time? 2 minutes. Okay, so real quick.
Yeah, I'm David Morris from Ames Research Center, and mine's more a comment than a question, although the panel may want to react. And that is just to remind everyone how different these objects are from the moon. Eros is 1 million times smaller than the moon in mass, and the objects we're talking about are almost another factor of 1 million smaller than Eros. I really wonder if we ever are going to want to put an astronaut on the surface, whatever that means. I think we should think in terms of telerobotic operations, visits by astronauts, but as was clearly said, you're never going to walk on the surface of one of these small, accessible asteroids.
Thanks for the comment. Bill?
Earlier in the day, we saw some presentations about taking the spacecraft and possibly tethering it to the asteroid and docking with the asteroid in some fashion. That takes time to characterize the gravity field to equal the trajectory to land. In your experience, how long did it take you to feel like you had a characterization of the gravity field of the asteroid before you felt comfortable with having your asteroid go in and land? Did that take weeks, or could you do it in days?
Days, no. I don't think so.
On Rosetta, we have an orbital phase that is between 6 months and 1 year. And we let the comet drive the spacecraft into the inner part of the solar system to gain power, because when we meet the comet out there, we don't have enough power. And so we come back to that problem. Anyhow, it takes a long time.
So, weeks at least. Yeah.
A matter of weeks. Okay, I think unfortunately we don't have any more time for questions and discussion, so carry on to the next panel discussion.
Thank you very much. Great, excellent, stimulating discussion. Certainly more time for questions later at some of the other breakout sessions or perhaps this evening.